Before we start this video, we advise you, following contents require a heavy physics background. So I advise you to put your thinking cap on. Do you have your thinking cap, Chris?
Yes, I do, Eric. Let's put them on.
Okay, let's put on our thinking caps. Right here. Oh!
Let's do it.
And he prays.
Do your homework! What? Do your homework! Oh god. I guess I should really start my physics project. Oh. Hey Chris, what's up, man? Oh, what? No, dude, I gotta do my physics project. But you're having a party, okay. Okay. Alright.
Yeah, Eric. It's Chris. Yo, what you doing, man? Yo, dude, come over to my house. I'm having a party, man. Dude, don't do physics. That's so lame, man. It's so lame. Okay. Yo, you coming? Eric's gonna have a great night tonight.
Dude, yo.
Hey.
Hey, what's up, man?
Not much? Yo, man.
Where's the rest of the party?
Oh, dude, they're coming later.
Like, they're coming later?
Yeah, dude, it's a two-man party right now.
Two-man party.
Yeah.
Okay.
Yo, dude, you look super tired and super thirsty.
Yeah, I kinda am, yeah.
Yo, have something to drink, man.
Oh, dude, thanks. Yeah, thanks, man.
Yeah. Good stuff, right?
Content's funny, but yeah, okay, sweet.
Alright, yo, let's head downstairs. That's where the real party's at.
Okay, let's go downstairs.
Yeah.
Alright.
Let's go. Welcome to the party.
Dude,
Yeah.
dude, where's the party? Dude, why do I feel so tired, man?
Oh, dude, take it easy, man. Take it easy,
okay,
bro. Take it easy.
fine.
Yo, just take it easy.
Dude, like, but seriously, man, you said there was gonna be a party. There's like
Oh, dude, don't worry
an
about
empty,
it.
creepy room.
Dude, don't worry
Dude,
about
I feel kind of weird, man. I'm getting a headache, and like I think I'm gonna pass out or something. Ugh. Oh, where the hell am I? Oh. Whoa. Yo, who's over there?
Attention. Bases pumping.
You're in my laboratory. Who in non-Euclidean space are you?
I'm Eric Park. I'm Physics 12 student of Dr. Schultz. Who might you be?
Stephen Hawking.
Man, you're Dr. Stephen Hawking? Dude, I don't even know how I got here. I was just at a party. My friend gave... Never mind. Okay, I guess since you're here and all, I guess I'll start my physics project. I really need your help, though. I chose my topic as gravity. I bet you're like, I don't know, like a rocket scientist when it comes to that.
Ha ha ha. Well, Eric, out of the kindness of my heart, I will help you for no compensation whatsoever. But, Eric, you're going to have to go against gravity and do some work. Ha 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 ha. Ha 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 ha.
Anyways, how did people started studying gravity? Like, I don't understand. What is gravity to begin with, huh?
Gravity is the attraction force between two masses in space. Understanding Newton's theory of gravitation and Kepler's laws of orbit provides answers to how the planets and stars move and stay in orbit.
Oh, I know that story. You know, like how Newton, you know, wakes up one day, you know, apple falls on his head, and after all, he invents gravity and calculus, travels time, you know, all that crazy stuff.
Not quite. Newton's observation of falling objects posed an interesting question. Was the force responsible for the apple's fall the same force responsible for the orbit of the moon and other celestial bodies?
Really? Is it really the two same forces that act the same way in two very different objects up in the sky and down here on Earth? I find it hard to believe.
Yes, it is. Newton proved this through using Kepler's laws and circular motion, which was purely based on data and observation. Newton also linked this with his idea of dynamics. Let's assume gravity is the force responsible for centripetal motion. If we equate the force of gravity and centripetal force together, we see that variables cancel out. Look, Kepler's third law is on the right side. This equation proves that gravity is the cause of centripetal motion. This can be used to find the mass of any heavenly body, such as my own. Ha 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 ha. We can also find the radius and period if given other variables.
Okay, so let's say I know the radius of your anus and the period of your anus. I could find the mass of the sun.
Yes, this is true.
So you're telling me I could find the mass of the sun by combining the two equations together? I mean, I would end up with a new equation of mass equaling to 4 pi squared over a gravitational constant multiplied by the orbit of the radius of 2.87 to the 10 to the 12 cubed over the period of 8.68 to the 10 to the 25th squared?
Precisely. It should be around 1.96 times 10 to the 30 kilograms.
Okay, then could you explain to me why the little g, the gravity, on Earth has value of 9.80 meters a second squared?
Once again, Newton derived the value of g from Galileo's observations. Newton hypothesized that weight was caused by gravity. Let's look at the force of gravity and the force of weight. The two masses cancel out. If we plug in the mass of the Earth and its radius, we find g is equal to 9.80 meters per second squared.
But then I remembered, g isn't always the same.
Yes, Eric, it changes with altitude. Remember to add the additional altitude before squaring the radius. This shows gravitational field strength. An interesting thing about gravity is that if you are infinitely away from an object, gravity has no effect on you.
Alright, so I get the fact that gravity is an attraction force of a mass. That's why things fall. But what about orbit? How can it stay in orbit if something is falling?
Our protagonist Newton set forth on a thought experiment. He imagined that a cannonball shot out of a cannon would fall at g. However, if a cannonball was shot out fast enough, the ball would continuously fall as the curve of the Earth curves away at the same rate. Therefore, the ball is falling. It's just never slow enough to hit the Earth. This is known as perpetual freefall.
Okay, I think I have a pretty clear understanding now. I have one more question. What about energy? Is it conserved in space as it is conserved in the ground? And if it is, how is it related to the orbits?
Absolutely. The total energy of the celestial bodies are no different than the total energy of an object on Earth. The kinetic energy, which is 1/2 mv squared, added to the potential energy. However, in this case, the gravitational potential equation is needed due to the gravity and the height both being the variables. Here I will go on a little tangent. If the kinetic energy is greater than the potential energy, the total energy sum will be positive, meaning orbit will not be established.
So does that mean if the opposite happens and the total energy sum is negative, the object will stay in the orbit?
Precisely. What do you suppose if the kinetic energy and the potential energy are equal to each other, though? The body will establish the flight trajectory of a parabola, and you will be able to find the escape velocity. The escape velocity is the velocity needed to escape a central mass that exerts gravity. This can be either on the surface of the planet or in orbit around the planet. For example, let's say we are trying to escape the surface of Mercury. We know that the total mechanical energy equals 0, and therefore we can rearrange the equation.
Plug in the radius and mass of Mercury, and that is the escape velocity.
Oh, cool. Is there anything else I should know about?
Yes. You are familiar with work and how it is found, right? It is found by measuring the area of a force versus radius graph. However, integral calculus is needed to solve for work. Well, I don't want to force you to do this. Ha ha ha. You also need to know about other contributions to gravity. Albert Einstein contributed that gravity is in fact a vector field effect. He speculated that gravity is the result of mass warping space-time curvature, and that masses orbiting fall into this curvature. Then, of course, we get into black holes, which have a gravity field strength so strong that light cannot escape. We also get into the fact that gravity can be so...
Whoa. That was way too much info. I'm just wondering, how'd you figure out all this?
Well, Eric, the view of science is very clear when standing on the shoulders of giants.
Oh, whoa. Dude, oh, hey, Chris. Dude, where's Stephen Hawking? Dude, never mind, man. Never mind. Okay. Dude, how long was I out for? How's the party? Is the party even here?
Yo, dude, nothing went on, man. Like, the party was already here. They went home. It's like 1 in the morning now. Now, when you weren't out for that long, I guess. I don't know. Maybe 5 hours.
Okay, thanks, dude. Oh. Dude, why are my pants off?
Remember, physics is fun.